Welcome to Air Quality Matters, and this is a conversation with Max Sherman. It's hard to overplay the impact Max has had on our sector. Even a cursory look at published papers on airtightness and infiltration, air quality, or ventilation, it's no surprise to see Max as an author, co-author, or cited at some point in the work. He completed his physics PhD in 1980 on air infiltration in buildings and went on to be a senior scientist at Lawrence Berkeley National Laboratory in California, retiring in 2016 as senior advisor, where he ran a research group for over 30 years. He has been a long-standing servant to developing standards with ASHRAE. He's a recipient of the Distinguished Fellow Award, Environmental Health Award, and Exceptional Service Award. He is a former member of the board and currently Vice Chair of 241, a standard on the control of infectious aerosols. He's a member of the EPA's Clean Air Act Advisory Committee and has been a long-standing participant and contributor to the International Energy Agency's Annex on Infiltration and Ventilation, the AIVC. It was an absolute pleasure to talk with Max. We discussed the origins of the term adequate ventilation and acceptable air quality, his work over the 30 years at Lawrence Berkeley National Labs, 241, indoor air quality, of course, and much more. Thank you for listening. This is Max Sherman. So if you take a look at regulations or codes of practice almost anywhere in the world, you see two words popping up very frequently, and they are the words adequate and acceptable, and they seem quite fluffy and bland. Why do we see those words, Max? And how would you define adequate or acceptable ventilation or air quality?
That seems like an easy question, but actually it's a trick question or half a question, because you have to define what you want ventilation to do before you can determine whether it's acceptable or adequate. It's not like providing oxygen. We know we have to provide a certain amount of oxygen to live, but we don't have to provide any ventilation ostensibly. After all, if you look at spacecraft or submarines, there's no ventilation and they get along just fine. So you have to talk about why you are ventilating, and there's lots of reasons why you might want to ventilate, thermal comfort, things like that. But I think today we're really talking about indoor air quality, and that's the reason that we want to ventilate. But that itself isn't well defined either. What is indoor air quality? What do you want to do with it? That's changed over the ages. Ventilation has existed before there were human beings. If you look at insects like termites, they have to ventilate their hives in order to survive or they'll die. And they figured out a very good way to do it, although it took billions of years for them to sort it out. And we don't quite have that amount of time. So what is it that we want to do with ventilation? Historically, people ventilated for only one reason, and that was to ventilate for fires. They had a fire inside, they had combustion, it produced all sorts of bad stuff, and they figured out rather quickly they want to get rid of that bad stuff, so that they ventilated. That was sort of the traditional way of doing it. The Egyptians learned that the slaves that cut their stones died rather quickly indoors. It probably was silicosis from what they were doing. They didn't know that, but they did know that they were a lot better if they ventilated the spaces or moved them outdoors or to lean-tos. So we figured out this ventilation thing very slowly and not necessarily the right way. We didn't sort of apply science to it till maybe the 19th century. And in 19th century in England, they actually started to look at it scientifically, mostly because Houses of Parliament were, in their words, rank and pestiferous. And so they started to figure out how to ventilate them. And they did some science and they figured out how much air would keep it from being rank. And then later in the 19th century, people like Florence Nightingale figured out that if you ventilated, you decreased the amount of infection that you saw in certain wards, particularly in wartime, which is where she had her most experience. So at the turn of the 20th century, we were ventilating more for health than anything else. But mostly in the 20th century, odor was what we ventilated for. We ventilated, if it didn't stink from ourselves, we figured it was ventilated good enough. And so that became the definition of adequate ventilation. In the 21st century, we've actually turned to health as the bigger provider of the bigger driver for ventilation. And so that's kind of what we look at things now today is what are the health impacts? And so that indoor air quality includes all sorts of health impacts. And that's kind of where we got to where we are today.
Interesting. And so when you start talking about people's perception of odor, is that where we hear terms like likelihood of discomfort?
That's basically right. Discomfort can mean odor. It can also mean irritation. So some things irritate our eyes or throat, and that can be discomfort. We can also talk about thermal discomfort, but of course, I don't think we're talking about that here. We're talking about odor and irritation as discomfort. Many odors are pleasing, and people don't mind if they smell those. So we're talking about the ones that are displeasing. And the biggest odor we face indoors typically is human body odor. And that's often the one that ventilation rates have been based on in the past at controlling human body odor.
And those controls of body odor, that's where we started to see standards like half an air change an hour in a residential setting or 3 or 4 air changes an hour in a non-residential setting. They were ventilation rates that were determined to provide a certain percentage of people that wouldn't complain of discomfort. Is that kind of where we got? Because I'm guessing 40 or 50 years ago, we weren't using CO2 monitors, right, to measure the indoor air quality in spaces. So standards for air renewal had to come from somewhere, I guess, when we started trying to translate air quality outcomes to ventilation standards.
That's right. But most of it came early on from engineering judgment that people were in buildings and they said, it just seems okay. And it's this much ventilation. So that seems okay. And it's not to put down engineering judgment. That's often the very first thing we can do and quite useful. It's not exactly science. The first science probably came in places like Kansas State and from people like Ole Fenger, who actually studied how much ventilation it took to dilute body odor and came with a number, something like, a few liters per second per person, from 2.5 to 7.5, depending on whether you wanted the first impression or the steady state. But they put people in chambers and had people smell and developed a little bit of science for odor. And that was reasonably well developed by the late 20th century.
And how have you seen the focus shift in our understanding of air quality over the last, say, 20 or 30 years? Because there's been a dramatic shift in what we consider the built environment. We've seen several fuel crises which have changed the way we try and seal the envelopes of our building. Ventilation is clearly scaling the ranking of importance in the built environment. And we're at a place now where we're really starting to consider the complexity of the air chemistry and the particulates. How's that progressed? And how have organizations like ASHRAE that you've been involved in taken on board that change over that period of time?
So there are two threads to follow here, and there's some tension between them. Starting in the 70s with the first oil shock, we realized that energy was a big deal and that we had to do all sorts of things to do it. And buildings were leaky and there was lots of air, and a quick analysis shows that that's a lot of energy that you're wasting. So there was a whole stream of work looking at tightening up buildings, reducing air leakage, reducing the energy associated with them. At the same time, though, that you have to look at the indoor air quality. And if you're reducing the amount of air you're getting, that could impact indoor air quality. And by the end of the 20th century, 25 years ago, we began to realize that health was a big important thing, and it wasn't just odor. And we started studying how much air you needed to try to get healthy buildings, not just low energy buildings. So the tension between low energy and health has been with us for quite a while now, and it continues on. ASHRAE has both those things going on. Its first standards, which its standards are numbered 62, 62.1 for commercial institutional, 62.2 for residential. Those standards began looking only at comfort and indoor air quality, but in the 70s, they started to change and reduce the numbers quite a bit for energy purposes. And since that time, there's been this duality has been going on where the standards go up and down depending on the science involved. So that's been a continual thread ever since then.
And when you say they go up and down, have we seen quite a shift in what we consider acceptable ventilation rates, for example?
Going by ASHRAE, yes, we have, because sort of numbers like 7.5 liters per second per person, or 15 CFM, as the old English used to call it, were numbers between that 15 and 25 were numbers that were used 100 years ago. Then when the energy shock hit and ASHRAE decided to do it, it went as low as 5 CFM, or 2.5 liters per second per person. So that's quite a huge shift. Now they're back up to other numbers, and folded into that was our understanding of things like smoking, which had a huge impact on the discussions, at least, of what these numbers should be.
Yeah, that's interesting, and it'd be interesting to see what this period of time does, because we have two tensions at the moment. Obviously, now we have disease control in the frame very much at the forefront, but we also have sustainability and energy efficiency really driving things. So that those tensions haven't gone away, have they? Really?
No, they haven't gone away. They're still around, but I think we know more now, so that we can resolve those tensions in a win-win situation much better than we were able to. Back in the day, we didn't really know why we were ventilating. We knew vaguely it had something to do with indoor air quality, and other than human body odor, we didn't have any quantitative numbers for what we should have. We're starting to get those now, and learning about contaminants and pollutants and what's important and what are the ways to control them other than ventilation, so that you can optimize in an engineering sense to get good indoor air quality and energy savings.
Yeah, and I think ASHRAE probably has, and actually probably it might be worthwhile you explaining who ASHRAE is, Max, for listeners that may not understand that organization.
So, ASHRAE, the American Society for Heating, Refrigerating, and Air Conditioning Engineers, handles sort of the built environment, the engineers that handle the indoor air and therefore the energy associated with conditioning that indoor air to be healthy. Willis Carrier defined air conditioning as the conditioning of air for thermal comfort, indoor air quality, moisture control, and all sorts of things, not just for cooling as we generally use the word today. It was actually formed in the late 19th century, and it's been around well over 100 years, and has been looking at this since then. It's the third standard I believe it wrote was on ventilation. So it's been around a very long time. It has a foundation of lots and lots of volunteers who write its handbooks and write its standards. And that's who ASHRAE is and has been. It's a professional society for the engineers who do it. There's a somewhat similar organization in the UK called CIBSE, and they were actually both founded at about the same time.
Interesting. And you personally, you ran the Lawrence Berkeley National Laboratory research group for nearly 30 years. What kind of work were you conducting over that time, and how did you end up in it's LBNL, I think, is the abbreviation? Is that right?
That's right, Lawrence Berkeley National Lab. Yes, so I ran a research group for over 30 years. And we were doing public sector research, mostly funded by the Department of Energy, to look at how to save energy in buildings. My own group tended to focus on smaller envelope dominated buildings. So we looked at things like airtightness and conduction through envelopes, and um, then that led to some of my interests in ventilation and indoor air quality. But the group itself focuses on saving energy through building efficient or retrofitting buildings, particularly residential scale buildings, although some of the issues are pretty general. And I did that for a long time till I retired a few years ago.
And what drew you to that work originally? What was the kind of trigger for getting into building energy and ventilation?
Well, that's a bit of a long story. So I was a graduate student at Berkeley in physics, and some people have a calling when they're uh, in university, and they know what they want to do. They feel a pull and they have a passion. I was more generic than that. I knew I wanted to do something in the hard sciences. I wanted to do something important, something that was beneficial, but I didn't have a firm idea on exactly that was. It's kind of the way I roll. I almost always have a really good plan B, but I let plan A present itself to me along the way. So in my second year as a graduate student, this is a time when you kind of have to decide what your dissertation work is going to be, which sort of determines where your career is going to be. And there's a course that's typically taken. I don't remember what the title is, but it's really trolling for graduate students. The professors come and they give a talk on what their work is and what you could do if you joined them. And they're looking to encourage people to join their group and help them do their work. And I was fascinated at that time by Art Rosenfeld, who was a physics professor. He had completely changed his career. His main career, his first career as a physicist, was in high energy physics. He was part of the group A that did a lot of the fundamental work there. But as he came and talked to us, he said he's changed what he's done because he's realized this energy crisis is going to be important for generations, that it was something that the engineers of today were completely mucking up and had no idea what to do, and it needed some fundamental thinking such as that physicists did. And that's what he was doing, and he wanted people to come help him. And that attracted me. So I went and talked to him, and he kind of gave me a job. And so I went and sat actually with the group that did indoor air quality, but I wasn't doing indoor air quality. He gave me a machine, a tracer gas machine. He said, go figure out what to do with this and what it means. So I went and I did that. And I started looking at airtightness, or infiltration, I should say, and realized that that was a huge amount of the energy that went into buildings, and nobody at that time knew how to measure it, and nobody at that time knew how to model it. And I said, oh, well, I think I can help along these lines. So I started my graduate studies looking at airtightness, how to measure it, how to model it. This was when the blower doors didn't really exist. They were something that was being played with in Sweden at Princeton, but they weren't a well-known thing. Um, and nobody had models for how to do it. The state of the art was called the crack method at the time, where you measured the length of cracks and multiplied by magic numbers until you got something. And of course, it wasn't very right. So I started measuring things with my new toy, and finding out that crack method didn't work, and trying to figure out the physics of what's involved. And that's what my dissertation was: air infiltration in buildings, because I put together the measurements and modeling. So
And
for a decade,
for context, Max, when was this? Like, because we
this
think
was
of
the late 70s. This is the
yeah.
late 70s. So mid to late 70s. So I spent the late 70s and early 80s looking at airtightness and studying it, and measurement methods and modeling methods, and pointing out how much energy there was. And things started to take off. People began to pay attention. People began figuring out how to make buildings tighter, and they could quantify their work with the blower door. in terms of tightness, and they could see what that was in terms of energy and actually ventilation in terms of modeling. So that's what I first did. But by a decade later, I began to say, okay, well, that's going well. It doesn't kind of need the same basic foremost fundamental research that I do anymore. It now needs the people who can take the next step and begin to turn this into practice. But it occurred to me that if we just kept going in this direction, we could make buildings very, very tight, and then there was going to be very little infiltration. And what was that going to do to the indoor air? Because it was cutting down on ventilation. So I started to look at ventilation and figuring out how to determine what minimum ventilation rates should be and how to get them. So that began my interest in mechanical ventilation, because we didn't do mechanical ventilation in homes, and only in really large buildings were there mechanical ventilation systems, because we figured there was enough air. Air would leak in and out, and if people didn't like it, they could crack a window or something. That was the philosophy. So in the 90s, I was looking at ventilation and trying to figure out how much was adequate ventilation, which was something that wasn't really sort of known too well from any scientific basis. There were numbers like half an air change or a third of an air change or 10 CFM per person or 10 liters per second per person. People had numbers, but no justification for them. So so I was working on the 62 committee during the 90s, which was both residential and commercial. And I thought we had pretty good rules then for commercial, but terrible ones for residential. So we split them in two, and that's when the residential one, 62.2, was created in ASHRAE. I became the first chair of that, and we worked quite a lot to try to get a standard that would be a minimum ventilation rate based on engineering judgment. We still didn't have a scientific basis for the numbers that we were using, but people kind of had a feeling about them. But at least we could describe how to get that number if you didn't have enough infiltration, which presumably you weren't going to have, because we're going to be very good about tightening all that up. So that's what I did in the 90s and the next several years. But then it became clear that we still didn't know why we were ventilating. Andy Pursley, from a well-known person in ASHRAE, always used to say that our standards were ventilation for no particular reason, because we didn't know why we were ventilating. We kind of thought it had something to do with air quality. Well, at the turn of the century, ASHRAE turned its attention more towards indoor air quality and health. It had been a controversial thing, and so it was kind of avoided to speak of it directly. But after the turn of the century, we began speaking about directly in ASHRAE, and the interest was, well, what's important? Clearly, there must be some important contaminants and some unimportant contaminants, and you have to control the ones that are important and not waste your time on the ones that aren't. So we had to figure that out. And nobody was doing that job too well. The norm in the health field was to look at things contaminant by contaminant and set threshold levels that you should always have below this, but 1% below this was fine and 1% above this was unacceptable. That isn't real life, isn't like that. You can do that in regulation. It's a way to regulate things. It makes some sense, but it doesn't make scientific sense, especially for chronic contaminants. You might, for highly poisonous ones, have a limit, but for chronic ones, not so much. So I wanted to look at that, and for several years I tried to look at that, and didn't get much funding to spend much time until the crisis of 2008, when there was a huge recession and the government decided it had to spend money to get the country out of recession. Some of the money it spent was on research. And since the Department of Energy isn't really good about adapting to things quickly, they wound up sending us more money than they gave us jobs to do. And I had no problem knowing what to do with that extra research money. I began to look to answer this question of what contaminants were important and how could we compare them to each other. And that was when the idea of being able to find the relative amount of harm that exposure to different contaminants came
Right.
about.
So that was where you started to join the dots between ventilation rates, actual air quality outcomes of various pollutants, and that linking that to what we now understand today as DALIs, and the important work that you started there around DALIs, because DALIs are the link to health budgets and access to other mechanisms that aren't open to the engineering and built environment at the moment. Because at the moment, when you avoid air quality and health outcomes, you miss a huge opportunity to unlock resources to enact change. And that all started from that joining the dots around air quality, DALIs, and harm and outcomes. Is that right?
That's right. That's what I was trying to do back then. Obviously, we were not experts in health. There were plenty of those things there, but the people who understood health knew nothing about buildings or energy or things like that. And I thought it was important to do that. The most fun parts of my career have always been when I've operated the boundaries of disciplines, of finding something of value in combining different things. So that's what I set out to do. And DALIs are disability adjusted life years. It's a measure of harm to a human, and it's not something we invented. They have been around a long time. They were used not in this context before, but that was my goal, is to try to make the connection between indoor air quality and DALIs, because that allows a quantification. Economists tell us how much a dolly is worth in dollars. And as soon as you can do that, you can then make trade-offs. You can optimize. You can decide how much you want to spend to get what kind of effect. So I set out to do that. And I used a postdoc to scour the literature to find out what did we know about harm from exposure to contaminants in the indoor air. And so we scraped we scraped all of the things we could find, and we put together a way to do this. I expected that somebody had done this before. It seemed pretty straightforward, but nobody had even come close, because the disciplines involved are all inward looking, not outward looking, and hadn't thought about doing this. So in 2010, 2011, 2012, we published a series of papers linking exposure of common indoor contaminants to harm, and in quantifying it in terms of dollies.
Yeah, really interesting. And I mean, for me, I started my career in the health service, and we were very familiar with DALIs in a strange way because of smoking campaigns. They were a direct translation of disability adjusted life years. I don't know if it worked in America, but certainly everybody over in the UK would remember that each cigarette cost you 7 seconds of your life. That effectively was a direct translation of the harm an activity causes you at a population level. They could translate that into early death or cost to the health service. And what used to happen at a public health level in the UK certainly was, but every time you went to the GP, he would ask you the question, do you smoke? And if you said yes, then the very next question would be, how many do you smoke a day? And if you smoked 20 cigarettes a day for a year, you would have what was called a pack year. And they would add up the pack years of all of their patients in particular areas, and that would translate effectively as a DALI to central government to understand how to resource that area from a health perspective or from an anti-smoking perspective. And big data before big data, really, an amazing public health public health piece of work. And I guess that's what DALIs translate really well into, is that population level translation of risk, isn't it?
That's right.
They
That's
provide you with
exactly right.
yeah, yeah. Um, you mentioned you were looking at airtightness in the in the 80s. I think you were probably one of the first people to attend AIVC conferences as well. I mean, again, maybe for people that don't know the AIVC, as you've been there from the very beginning, would you maybe describe a little bit about what the AIVC was and what it's now become? Because you've been there for that whole journey, haven't you?
Yes, but I have to even start before then to understand it. The AIVC is actually a piece of the International Energy Agency. The International Energy Agency was formed as a counter to OPEC. For the oil consuming countries to try to work together to reduce their reliance on it. And it's broken up into many, many different pieces. And this one particular piece was, at the time when it was created, called the Air Infiltration Center. Ventilation wasn't part of it because it was all about reducing the energy associated with infiltration, and it was part of the R&D arm of the International Energy Agency. The AIC was created in 1979, and in the International Energy Agency, members are countries rather than people. So there are 22 members in the group above the AIC, so there can be at most 22 countries involved in the AIC. And the first conference was in 1980 in the UK. On the grounds of Windsor Palace, actually, interestingly enough. And that was the first conference I attended after getting my PhD. In fact, we had a rule that graduate students couldn't travel internationally at the time, so they had to rush my signatures on my PhD in order to get it done in time for me to go to the conference. And there were only, I don't remember, maybe 20 people at that conference. And I have been to most of the conferences since that time. In the late 80s, I think it was decided that ventilation was sufficiently important and was itself an energy user that the AIC should be upgraded to the AIVC and include the Air Infiltration and Ventilation Center. Its major purpose is as a dissemination body. That is, there wasn't a lot of research going on in individual countries at the time, and this was a way of coordinating it and putting it together in technical notes and other publications so that people could use it all over the world and benefit from the knowledge that the member countries had. In the beginning, it was sort of a brick and mortar institution. The countries put in money. There was a staff. There was some head of center, and there was a library. All these sort of physical things. It has since become far more virtual than that. There is no brick and mortar place. Countries mostly contribute time and effort and only a very small amount of money to keep things going. So it has evolved in the 40 plus years since it started.
Yeah, and it's the fifth annex, isn't it? So I think it's one of the few annexes that gets a rolling mandate that it has to reapply for every 5 years, isn't it? Isn't it?
Right. Well, now you're getting into the sausage making of how the IEA works. There are implementing agreements where a bunch of countries say, we're going to work on this general topic. And then within the implementing agreement, there are specific annexes where a specific project is proposed and countries agree to join and work on this project. Mostly those are 3, 4, 5 year projects with a clear stopping point. But in the case of a dissemination center, there was no clear stopping point. It wasn't intended to just be 3 years and done. So it goes through a reaffirmation process every few years to re-up it, but it's not intended necessarily to end at any specific date. It should continue as long as it's useful in being there.
And it's produced some very valuable work. I mean, it was an organization that I started to pay some interest in maybe 10 years ago or so. And I think I saw your early work on the DALIs. back on one of my first workshops that I attended. An Ireland at the time wasn't a member of the AIVC, so I'd spent several years trying to convince the local authorities here to join, and I think it's been a great benefit to us locally here, because even the airbase database is a phenomenal research tool. If ever there were historians out there looking to see how research has progressed over 40 years, go and have a look at airbase. It's unbelievable. I think it's like 22,000 publications or something on there. It's unbelievable at this stage.
Yes, it was one of the major resources early on because people didn't know where to get information on this topic. It wasn't easy to handle. So the center itself had copies of everything and had an electronic database and said, okay, here's all these interesting research topics that people may want to look up to get knowledgeable about it.
So ASHRAE and AIVC do differ. You're still involved as a guest board member with AIVC. That's right, and you're still involved today with ASHRAE. Most recently, I think of note has been the 241 standard. I think that's probably an interesting story for people to hear, both what that standard is and perhaps the unusual circumstances that were brought to bear to get it up and running. You were vice chair of that group, is that correct?
That's correct. But to rewind a little before that, so when when COVID first hit, there weren't a lot of people on the building side who were ready to deal with a pandemic such as this. And the first thing that happened was that the CDC and WHO came out and said that, well, COVID isn't an airborne disease, so we do the things like we normally do, wash our hands and sanitize surfaces and things like that. Well, those of us who were familiar with how aerosols work could see very clearly it had to be an airborne disease and that these guys were wrong. And there were also political reasons that they might not want it to have said it was an airborne disease. But so I was one of the 230 some people who signed on to an open letter saying, hey, it's an airborne disease. The data is very clear. We have to treat it that way. We have to do stuff. Well, ASHRAE as a body bought into that and created what was called the Epidemic Task Force. This was a group of people to very quickly, ASHRAE is not good at doing things very quickly, but the purpose of this was to very quickly come out with guidance that people could use of what they should do in buildings to reduce their risks. And the Epidemic Task Force was chaired by an ex-president of ASHRAE, Bill Bonfleth. And he asked about a dozen of us to be part of it. And so I was on the Epidemic Task Force. And each task force member was the chair of a task group to do some specific thing. My specific duty, I was chair of the residential task force because of my history working in the residential sector. And altogether, there were about 150 people who contributed to the effort in these different working groups. So my working group was to come up with, well, what should you do at home? And I was very motivated to do something very quickly because people were sending people home, not unreasonably so. They didn't want offices and things. Well, if everybody's going to be at home, we better do something to keep them as safe as we can at home. So we very quickly came out with a set of recommendations, as did all the task groups. And there's still a website on the COVID-19 sub website of ASHRAE has links to all of these recommendations, which are quite extensive. So we operated for about a year and a half, coming up with better and better guidance, general principles. The idea, was, well, what could you do with your HVAC system? What could you do with ventilation and filters and all these other things to keep yourself as safe as possible? So that was the Epidemic Task Force. It was focused on COVID-19. And then ASHRAE sort of realized that was going to have to do something to codify this for the long term. And at about this time, ASHRAE was approached by the White House. And the White House wanted a standard very quickly because it knew in approximately May of 2023, it was going to get out of the COVID business and wanted the public, the more public sector to take over it, and said, well, we want you to write a standard on what to do for general epidemic preparedness. And that was what became Standard 241, which is control of infectious aerosols. Those meetings happened in the fall of 2022, I guess, and ASHRAE committed to doing something quickly. Again, they're not good at doing things quickly, but we managed. Bill Bonfleth was again appointed the chair of that, and he asked me to vice chair. And there were approximately 50 people involved. It was a call for members. We had to put together a committee, and this committee, we decided it had to operate in a Tiger Team mode. For those of you who remember Apollo 13, that was what they had to do. They had to come up. They had lots of problems to solve. They put together teams to solve them. And failure was not an option, was their theme. That is, we're going to get this done at a certain time, and we're going to do the best we can, and everybody's got to buy into that. And
is this a new precedent for ASHRAE, Max?
It is a new precedent. Yes. It's a precedent, but not one that will be used that often, I imagine, unless we have other such global scale emergencies to deal with. I think we'll probably go back to the more normal quibbling that we do so well in ASHRAE. But for 241, people bought into that. They all understood that we had to get somewhere quickly, and then we could fix whatever we wanted to fix down the road. So something that should have taken about 4 years in ASHRAE time took 4 months. And 241 was approved as an ASHRAE standard in late June.
And there's some, perhaps to dive into it in a little bit of detail. I mean, I don't want to go line by line, but there are probably 4 clear areas, I would say, that have come out of it of interest. The first one being this concept of a infection risk management mode, that buildings going forward may have 2 modes of operation. I think that's an interesting concept, and one that you may find goes beyond North America as an idea.
Yes, I think it's quite generic and useful. The idea has several origins. One is there were many people who wanted us to tell them, when should you use these procedures? And we decided that wasn't something that an ASHRAE group could determine. That depended on many things. That depended on community infection rates, the kind of disease it was, what level of protection you wanted. So we were not about to tell you when to use these features. That would be up to the local public health people, the people on the scene who knew when it was time to require them, or for an owner of the building who wanted to decide when they wanted to turn on this extra protection. So we essentially said, we don't expect to see that here. We're going to tell you what to do when it's in this mode. We're not going to tell you when to turn on the mode. And this is part of the larger resiliency package. That is, it's resilient against an airborne epidemic. When that happens, this is one of the things you should do. And it's not the only thing you should do. We're only looking at the long range effects. We're not talking about when should you vaccinate, when should you put on masks, when should you separate people. We're talking about what happens in the indoor air with people who are not breathing directly on each other. So that's again a limitation that we put on ourselves.
So in hierarchies of control, it's the engineering controls part of the complete package. It's when you want to manage a certain risk, whatever you determine that risk to be. I mean, I'm guessing it could even be seasonal flu, right? If there are certain sectors that are very vulnerable, or certain parts of society that are very vulnerable, it may well be that that mode of operation is turned on for very specific subsets or for very specific reasons, or a global pandemic. God help us.
Absolutely, all of those things. You run an office full of people, and this flu season, and you may want to offer more protection to your workers. We're not saying you should or shouldn't do that. We're just saying here's what you should do when you've decided you should do that.
And is a little bit a part of that, because I think if you look at some of the kind of numbers, and we'll come on to clean airflow rates in a minute, but when you look at the kind of airflow rates that are in the guidance, they're quite eye-watering. When we talked earlier about this tension between the amount of air you move in a building and energy efficiency, there's some pretty staggering equivalent airflow rates in 241, isn't there? I mean, I think in some circumstances, up to 20 litres a second per person, which, in an office environment would be very difficult to achieve now, I guess.
Well, there are two diametrically opposed responses to that. First of all, some of the numbers that other people recommended were far more eye-watering than these numbers. We spent a huge amount of time coming up with a model in order to generate those numbers, a model that achieved a bunch of requirements to get those numbers. But they're only as eye-watering as you think if you are thinking in terms of providing with outdoor air. And one of the major points in 241 is that outdoor air is a way to do it, but there are many ways to do it, and you need to find the ones that make the most sense in your particular case. Filtration is a legitimate way to do it. Now, filtration doesn't get rid of gaseous contaminants like formaldehyde, but we're assuming you're doing all of that sort of thing anyway. That is, you're meeting minimum indoor air quality standards. These are just requirements for infection control. And putting in filters and recirculating air is not an eye-wateringly expensive, from an energy point of view, sort of activity. There's also things like sanitization with things like ultraviolet light, which requires no air but can be turned into equivalent clean air rates in order to do that. So it does not have to be energy intensive to meet this.
And I think that's probably, again, one of the big mental shifts that 241 has brought to the fore, and that is that there are a number of ways in modern ventilation of achieving air change or equivalent air change. But it requires engineering thinking. This isn't... we would have had a lot of responses during the pandemic to, well, something is better than nothing. And the risk is in the built environment that where there's money to be made, people will sell something, right? And when you're talking about mixing the modes of ventilation with air cleaners and UVC and potentially other types of products, you need to be clear what you mean by a clean airflow rate. So I think that's an important part of 241. It starts to set that framework to say, well, look, I may be achieving 2 air changes an hour in this classroom with traditional ventilation. If my target is 5 or 6 during a pandemic, how do I get it up there? I can't open the windows anymore. The ventilation system is maxed out at that stage. If I can't afford wholesale upgrade of mechanical ventilation, then what are the alternatives? Can I supplement that with some UVC or with some filtration? And I think that's a really interesting idea that probably will be taken up beyond 241. That I think in this period of time where we're trying to understand the balance between fresh air and energy savings, that those kind of solutions will offer up some kind of solution in that sense.
That's right. We did not want to limit the technologies that were being used in any way. So all of the standards that we could find which would work, we allowed people to use. And in fact, we wrote an appendix which was a backup standard. That is, if you had a new technology that for which there was no existing standard, you have to show that it's safe and effective. We were in favor of anything that could be shown to be safe and effective. So in the Appendix A of 241, there is a test method to demonstrate acceptable safety levels and then on how to quantify performance. And, if you have any technology, cosmic rays or a flux capacitor or anything you like, you can qualify it using Appendix A, and if it meets its safety requirements, and then you report its performance in accordance with that, and you can use that as well. We want it to be as open as possible.
I think that's good to hear, because I think indeed both flux capacitors and cosmic rays have been sold and tested by NASA apparently. So I think it's important that these, in fact, I mean, that was a brave area to walk into, because at the time, air cleaning has been quite a contentious subject matter to discuss, because the burden of proof wasn't clear for a lot of companies. You don't want to stymie innovation, but at the same time, you don't want to create openings that allow products that haven't been brought to the full rigor of testing into the marketplace. Was there some nervousness about having to deal with that part of it on ASHRAE's part, or was it a grasp the nettle thing? It's such a key part of it, we're going to have to address it in some way.
I think both those things are true. There was some nervousness because there were players who had innovative or emerging concepts that they claimed many things for which there was not necessarily independent justification. So we knew it would be somewhat contentious. On the other hand, we didn't want to exclude any technology just because we didn't fully understand it. We wanted to set the criteria for acceptability and not pick and choose. So in a way, setting the criteria was a way to not have to say we believe in this and we don't believe in that. People just have to demonstrate that they can do it, and then they qualify. So that was it. We knew it was going to be hard, and there are already criticisms of what we have done in there, but we think it's justifiable what we've done, and we hope it will be taken up and used.
And perhaps it's worth explaining to people a little bit about why it's contentious. There are air cleaning approaches that are have a removal effect on an environment. So filters are a good example of that. And the more effective a filter, the more particulates or pollutants it may or may not remove. But there are also other approaches that would use technologies that may change the nature of the air chemistry in the process of what they do, or indeed may add things to the environment in order to get an outcome. And it's that makes people nervous, right? Because it's air chemistry is a very complex thing, and actually testing it and even testing the effectiveness of products to remove viruses and bacteria from the atmosphere is very complex to test. So it's not that the scientific community or the regulatory community are being particularly obstructive. It's just really hard to assess and get right. Is that right?
That's right. So you can divide the problem a bit into active and passive technologies. Passive technologies are things like filtration that just remove things from the air. Active things put something into the air, and when you do that, then you have to know, well, what are the unintended consequences of putting that something into the air? And hopefully any products or byproducts it puts into the air are not going to be harmful. So from the safety side, you need to check that. The safety requirements for in 241 basically say that, okay, you have to you have to not put in ozone, you have to not put in these things, and you have to challenge your active approach with these following things and see if they produce any byproducts. Now, that doesn't cover everything there is to cover. It was deemed to be the best guess about what are the things are that could happen, and passing that safety test is no guarantee that there's nothing there, but it was what was considered reasonable. Now, on the performance side, what you're trying to do is remove the amount of viable pathogen in the air. And you can do that either by removing the pathogen or by making it no longer viable, such as with UV light. Now, we don't really care how it works, which one of those two things it does. We only care that it works. And so the test method requires a challenge with a particular bacteriophage. It's called MS2. And you show that you remove it. And we don't care how you remove it. We don't require you to prove that you killed it or it was deposited or whatever. We just say you do this test and you get this number, and that's the number you're allowed to use.
Really interesting. And I think perhaps one of the final pillars of 241, which I think is really great, is that you have to have a plan, right? That all of this stuff is great, but actually the standard requires a plan to make sure a building is ready, and that there are steps to check the systems are working as they should. And like that might seem obvious as a lay person, but it's very rarely done actually in reality out there, isn't it? That organizations and buildings and assets actually have a plan, or even a plan for maintenance sometimes.
That's absolutely true. I mean, you have to define what it is you're going to do when IRMM is activated, and what's going to happen and who's going to do it. And you have to put all those things in a plan so that whoever's in charge of pushing the red button and knows when to push the red, or knows how to push the red button, and what has to happen. So what do you do to your control system? Things like that. And if you're going to run in IRMM, you probably have enhanced operation and maintenance requirements. You have to write those down so somebody knows what to do. Now, in the case of an individual dwelling unit, you don't need quite that level of detail, but you do need to know what's going to happen. For example, one of the things that you have to have in a residential setting is the capacity of having an isolation space, because we presume that at some time you're going to have a sick person in there, and there'll be other non-sick people, and you want to isolate them. So you have to have a plan for doing that and what that means. And this is especially useful, let's say, in multifamily buildings where the owner may wish to provide this level of protection to his tenants. It's part of his advertising, part of his value added, but he has to tell them what to do when the red light flashes, or however it is he triggers them. So you have to have a plan, and you have to have done some planning ahead of time to design what the system is. In other words, how much air can you get, or do you want, of outdoor air? How much filtration do you want? Do you have centralized filtration? Do you have room level filtration? Are you using UV? Are you using flux capacitors? Whatever it is, you have to have evaluated it and explained how to turn it on when the time comes.
Yeah, interesting. And it speaks to, like any risk assessment, really, what your current level of mitigation is, what good looks like, and what that gap is, and how you might need to prepare for that gap and bring a building up to a standard it needs to be to hit 241.